First of all, thanks Thomas for the comprehensive talk about the Apex platform. My name is Siyuan. I'm a developer in World DataTorrent. I'm a committer of Apache Apex, and I built the Kafka input operator for the platform. First, I just want to give a little bit history about the Kafka input operator. In the Apex library, Apex Malhar library, we actually have two versions of Kafka input operator. One is based on the Kafka 0.8 API, and the other is based on the the new Kafka 0.9 release. The reason why we want to have two different versions is I don't know if you guys know Kafka. So the reason behind this is 0.8 and 0.9, and the API it looks totally different, and I feel the 0.9 API is simpler than 0.8 and is easier to use. And so in the long term, the 0.9, the operator built using 0.9 library would be easier to maintain and debug. So we have two different versions. So next, let's look at the features for the Kafka input operator. So both old one and new one has almost similar features. They are both fault tolerant. They are both scalable. They can scale up and down with Kafka partitions, and they both support multi-cluster and multi-topics. It means you can set topics you want to consume from multiple clusters. And they both support throughput throttle. You can limit how many messages you want to consume per second, and also they are both idempotent. As Thomas talked before, idempotent is very important in exact-once semantic. And also, they both support offset management. Offset management here means the offset checkpointing and the offset commitment. That's a key component to guarantee no data loss. And also, they both support one-to-one partitioning and one-to-many partitioning. In the old input operator, we also support dynamic partitioning, which based on the throughput, but it's in our test it's not very stable because the throughput itself could be unstable, and it also depends on how fast your cluster is. So we took it out from the new input operator. And also, they both support the customized partition. You can implement your own logic, your own algorithm or logic to do the partitions. And talk about dependencies. The old input operator, because it's using the simple consumer, so it uses both public and internal API, which make it there are some compatibility issues from Kafka minor versions. You have to pay attention for that. But the new one, it all depends on the public API, so it should be stable. According to Kafka community, it should be stable in major release. And they both support matrix report. Matrix report is so you can get some data through REST API from the application master. Those data are like throughput data, like message per second, per partition, per topic, or bytes per second that the input operator consumes. So the only difference is the old one is using the old Apex counters API, and the new one is using the new annotation that we introduced later. some notes about the old Kafka input operator. So the old Kafka input operator is using the simple consumer because only the reason is we support both. We support both simple consumer and high-level consumer, but only the simple consumer can deliver all the features that I talked about. The reason is the high-level consumer doesn't support customized assigner, which is a partitioner here, and it doesn't support sticky partition. It just do some internal logic to partition, but the problem with the old input operator is the simple consumer doesn't handle the metadata change. So we have to handle the metadata change in the operator code, which we don't like to do it, but we have to do it to implement those features. The metadata change here is, for example, there are some broker failures happen. The partitions hosted on that broker will be switched to other brokers. So then the simple consumer cannot handle those failures. You have to discover where the new leader broker is and reconnect to that leader broker to continue consuming data from that. Simple consumer can only talk to one broker. So if you look at the Kafka input operator code, in each Kafka input operator instance, there are multiple consumers, and each consumer talk to one broker. And there might be multiple partitions on that broker. So, but for those partitions, they just use the shared consumer object to consume those partitions. And we built this old operator like 2.5 years ago, and it's running, it's tested, and it's running in some production machine, so it's more mature than the new one. So some highlights about the new Kafka input operator we just released. In the new Kafka input operator, we use the assign API, comes with the 0.9 consumer class. The assign API is a very good replacement for simple consumer we used in the old input operator because we are still able to explicitly assign the Kafka what Kafka partitions we want for each input operator instance, and then inside the consumer, it handles the metadata change internally. So we don't have to worry about anything change on the broker side. We just need to tell the consumer class, okay, I want to consume from this topic and this partitions. So it's easier to use, but the only problem for this new input operator is it's very young. It's just two months old. It came out at the same time when Kafka released 0.9 API. So here's a workflow for two input operators. As you can see, the main workflow is the same. When the application starts, the application master will get the metadata information from Kafka cluster, like how many partitions are there for the topics you want to consume, and where is the leader brokers for those partitions. And based on different partition strategy, it will calculate and the metadata and the Kafka partition metadata. It will calculate how many operator instance you want to have, and then assign a set of Kafka partitions to each instance. So till now, the old one and the new one are same. But if you look at inside each operator instance, they are working differently. In the old one, because the consumer object cannot handle the metadata change, So in each operator instance, we have a separate metadata thread which monitor the metadata change in that thread. And if anything change, it will notify this consumer thread, okay, some partition has changed its broker, something like that, and ask the consumer thread to connect to the new broker to continue consuming data from the new one. But here in the new operator instance, we don't need to worry about the metadata change. It's all handled internally. It's all handled internally in this consumer object. So we just need one consumer thread to keep consuming data from Kafka. Next, I want to talk about the different partition strategies that we support in Kafka input operator. So the two most used partition strategies is one-to-one and one-to-many. One-to-one is for each Kafka partition, you have one Kafka input operator to consume data from that. And one-to-many is for each Kafka input operator instance, it could consume from more than one partitions. Depends on how many input operator instance you want to have and how many Kafka partitions there is. So this something you have to keep in mind is this one-to-n partition is a round robin. It's based on a round robin, so you can see all the Kafka partitions will be evenly distributed to Kafka input operator instances. So next, so what if they are one-to-one and one-to-many is not really what you want? You want to implement your own partition logic. Then we have this abstract Kafka partitioner class. Developer can just extend this class and implement the assign method. This parameter for this assign method gives you all the partition metadata. It's all the partitions for all the topics from all the clusters you want to consume data from. And also there are some, you can also override some useful method. For example, this partitioner method will be called when the partition action is done. And the process stats method is called when you have some stats reports from the input operator instance. Those stats include those throughput stats like messages per second and bytes per second, for example. So if you want to do some partition based on throughput, you can just override this method and do whatever you want. Here's some very important principle that I want to talk about. So all the one-to-one partition, either one-to-one partition or one-to-many partition, or you might want to implement your own customized partition strategy. All those partitions should be sticky partition. Sticky partition means only application master is responsible for assigning those Kafka partitions to each Kafka input operator instance. And when the Kafka input operator instance is assigned, they should stick to those partitions. They should not change all the time. The reason behind that is I will talk it later. So the Kafka input operator is a stateful input operator. It keep track in the memory. It keep track of the offset, and those offsets are useful to recover from the failure. So that's why we don't recommend you to switch partition in between the Kafka input operator instances. So next, I'm gonna talk about a key component in the Kafka input operator, which is the offset checkpointing and the offset commitment. This is a key component because with this, only with this, we can guarantee no data loss. So let's look at this diagram. So now let's assume. So this is, let's assume this is what a Kafka input operator is consuming data from Kafka. So at that time, at this time, the Kafka input operator is at this offset. It's reading data from this offset. And in the memory of this Kafka input operator, it also keeps the history window ID with the last offset for each window. Let's assume this input operator instance keeps the offset, history offset with window ID from window I to window J. Right? And then let's assume the downstream operator is at window K. So the window here is the streaming window that Thomas talked about. In Apex application, different operators has different process speed, so they could be in different windows. So the downstream window could be, so let's assume now this Kafka input operator is at window P, let's say, but the downstream operator could lag behind. It could be still in window K, let's say. So now, and those history data, it's in memory state for the Kafka input operator. And as Thomas talked before, Apex has this checkpoint mechanism happen periodically. So it will checkpoint those history data with including the window ID with the offset, and keep it in and checkpoint it in disk. And then let's so if at this time the Kafka input operator is down for some reason, so the Apex will bring the input operator back in another available resource and restore the checkpoint state from the persistent layer, and then it will continue from window K instead of the last left of window, right? So sorry. Because the history offsets are checkpointed and restored, the input operator will know where it needs to continue from.
Let's test the voice. Hold on one sec.
Yes.
Go ahead.
Can you hear me? Sorry guys, we have some network issue here. So I'm just gonna summarize this slide. So let's assume this Kafka input operator is consuming at this position, and also it keeps the history offset along with the window ID in the memory, and this state of memory will be checkpointed periodically by Apex. And so when this input operator instance goes down, and when Apex brings it back again, it definitely doesn't want to continue consume from this position, because the downstream operator just process till this position. So from here to here will be lost. So we want to bring it back at this state. Because the history offset along with the window ID are checkpointed. So when the Apex bring the instance back, it will restore those states, and then the new instance will be able to resume consuming data from this window. Another part is called offset commitment. So in Apex, there are a special event called commit window event, and happened in between the window boundary. So when the commit window happens, it means the Apex application master tell each operator that all the operators in that DAG has done processing data before window I. So when the operator gets that call back, it can safely, first of all, it can safely discard all the history data before window I, because the operator will never be back before window I. You don't need those history information. So the whole DAG has already done processing those data. The next thing it will do is it will save the offset with that window into some persistent layer. So in 0.8, those offset with committed window I will be reported to application master, and then the application master will use an interface called offset manager to save the offset, the committed window offset, into the data layer, into the data store, into whatever you implement. So this is how the offset manager interface look like. The update offsets is supposed to save the Kafka partitions along with the committed offset into any data store you want. And load initial offsets is used to store those offsets from the data store when the application start. And we have this interface because in 0.8.0 and 0.8.1 Kafka and consumer API, there's no way to explicitly checkpoint to explicitly commit the offset. But in Kafka 0.9, they provide a commit method in their consumer class. So the first part is still same, but the second part, each consumer instance will just call that commit method, and the commit method in Kafka consumer is actually save the offset into another Kafka topics, into another Kafka topic, and the topic will contain the application name. So this is very useful because sometimes you want to kill your whole application, and when you bring the whole application back again, you want to continue from where you left off. Sometimes you want to continue from where you left off. You don't want to continue from the very beginning or the latest. Question?
What happens if the topic you're saving, the offset to goes down? Because Kafka is itself possible to go down, right? So
yeah.
And is there only a single topic that you write to, or does each
I think there's
topic
still
write to one other topic?
So Kafka is Kafka has usually you have duplication for topic data. So if one, let's say if the broker that holds this topic data down, then a backup will pick up.
Okay, and is there a single topic just for the offsets, or does each operator have its own offset topic?
No, it's Kafka doesn't know. it's being used by Apex or other application, right? So we just give the application name to the consumer. We just use this application name as the consumer ID, and when you call the commit method, it just commit to the topic which contains that consumer ID, which is the application name here.
Got it. Cool.
So here's some important properties for this Kafka input operator. Initial offsets, where you want to start consuming, and you have to set the topic. And for the old one, you have to set the zookeeper. And for the new one, you have to set the brokers. And strategy is the partition strategy. And you can set the limit of maximum tuples you want to consume per each streaming window, for each streaming window, and then initial partition count is used along with the one-to-many partition. This is the how many instances of Kafka input operator you want to have. And then for the old one, you can set the offset manager. And for the new one, you can set the other consumer properties through this consume props. For example, if you want to set the decompressor, compressor, decompressor, or if you want to set the buffer size for the consumer, you can set the properties here through this. Last, I want to talk about something called Malhar Stream. So Malhar Stream is a new product in the latest Malhar release. They have this product called Malhar Stream, which delivers the same functionality as Kafka, but implement in their own way. The nice thing is to consume data from Malhar Stream, you can just use the same API as 0.9 Kafka client. So it's fully compatible. So we have tested our input operator with on top of the Malhar sandbox, and all the features are working except multi-cluster. And there are some slight difference if you want to use input operator to consume data from Malhar Stream. First of all, you need to use the Malhar Stream client library instead of the Kafka, the official Kafka one. And then in the cluster property to consume data from Malhar Stream, you don't need to set the clusters because the Malhar Stream client library handles those issues and figure out where it get data from. And also for the topic name, you may notice slash is invalid character as a topic name in Kafka library, but it's actually valid here in our input operator because in Malhar Stream each topic is just a file name in Malhar's file system, so slash is a valid character. And also we did some performance benchmark for our Kafka input operator. So those benchmark application is based on the Yahoo streaming benchmarks. So Yahoo streaming benchmark is it defines some process logic, and different platform implement the business logic in different ways. It has a Flink version, it has Storm version, and we also develop our Apex version. It builds the same DAG, process same data, and compare the numbers for each from each application. So for this Kafka input operator benchmark, we set up 4 Kafka brokers. We set up 4 Kafka brokers cluster, and we create a topic with 8 partitions. We use 1 zookeeper, and here's the hardware parameter here, and so those are numbers we get from the benchmark application. So for the old input operator, we can see we get like 900, above 900,000 messages per second, and each message is about 250 bytes. And for the new one, it's I just get this number yesterday, so the number is good, but it's supposed to be, according to Kafka community, the new consumer should be more efficient than the old one. So we should see the number bigger than this one. So we are still working on the tuning. So
this is per partition.
No, this is overall.
How many partitions?
8 partitions.
8 partitions.
And we are using one-to-one partition.
Got it.
Yeah. So each partition is like over 100,000 messages per second. Yeah. And that's it. Any questions? Yeah, please.
In your .8 library, you support compression schemes, gzip or snappy.
We don't support that, but you can have a downstream operator to do the compression or decompression. Because those are, I believe, those are high-level consumer features. Simple consumer doesn't support in consumer decompression and compression.
So the Apex containers to Kafka partition, is it 1-to-1 ratio, or you can have 1-to-many ratios?
You can have one-to-many. You can have one-to-one or one-to-many.
So each partition in Kafka, you can have multiple processes on Apex.
Oh, you mean each Kafka partition? No, each Kafka partition you can have at most one.
So you cannot have many to one Kafka.
There's no many to one. It's a distributed system. It's very difficult to coordinate which message goes to which partition. Yeah.
Yes, and also to notice that typically the limit is not on what one Apex partition can process, but what you can transfer over the network. So what we can do and what we have tested in production is that one partition in Apex actually consumes multiple Kafka partitions. So that is actually, this is how the connector is being used. There hasn't been a scenario where there was a need to consume a single Kafka partition by multiple consumers on the Apex side.
So there's an online question. Have you tried benchmarking with multiple partitions reading from Kafka partitions? Similar question.
Multiple partitions from reading from one Kafka partition.
From Kafka partitions. So the same question. So you could answer.
No, we haven't benchmarked that. Because we are follow the standards that the Yahoo streaming benchmark.
So this is 1:1. This is not one. This is not one.
This is all 1-to-1.
5 Kafka.
No.
Okay. Thanks.
Any questions? Okay, that's it.